So hopefully everyone can see that I'm sharing this proof that I wrote. I mean, not that I came up with or anything. Like, this is a very standard proof of this fact, but I thought it was worth everyone seeing it before we started talking about some of these sine limits that we're going to talk about today. So I'm gonna talk you guys through this proof real quick, just so that we can. And if you have any questions, please speak up or type something in the chat, which I do have up, so I can see the chat if you type a thing in the chat. And I don't know, I think I was gonna write like a less rigorous proof when I started writing it, so I wrote proof in quotations. It is an actual proof. It's not like a pseudo proof. This is an actual proof that the limit as theta goes to 0 of sine theta over theta equals 1. This is also available in Canvas. I made a new module that's actually, let me remind myself of what the module is called before I try and tell you guys. The module, where'd you go? Sorry, one sec. I think it's called like useful handouts in the modules. That's probably what I called it. Yeah, useful handouts. So this is the first handout. It's proof of the limit of sine x over x. So if you want this document accessible later on, it is right there in Canvas. As far as I'm concerned, not that I'm an actual teacher, you should never have to reproduce this proof, but it is something that's good to be aware of. So you can certainly write down the things if you want to write them down. You do not have to write down any of this as it's available to you, and you shouldn't have to reproduce it anyway. But let's talk through it. So this proof really depends on this picture, which is really part of a circle, right? So I'm imagining there's some larger circle here that this is a sector of. And when I say the word sector, I really think of a slice of pie, right? Like you've got a pie and you take a slice of it. So this is a sector of that. And so I'm going to say it's a circle of radius 1, so that this length OA and then this length OB are both length 1. And then from B, I drop a perpendicular to OA, and then I'm going to call that point C. And then from that point C, I'm also going to draw another sector. So this little sector with the red kind of part here, that's a sector as well of a smaller circle, where the circle would have radius OC or OP, whatever you want to call it. The thing to know there is that the length OC and OP are the same length. All right, so I think we've got everything set up. Oh, just a few trig things here in this particular picture. If you look at the triangle OCB, where OB has a length of 1, then sine of theta is opposite over hypotenuse, which is BC over 1, which is just equal to BC. And similarly, cosine of theta is equal to adjacent over hypotenuse, which is OC over 1, which is just OC. Also, my voice is already feeling a little tired from the hour of teaching I already did, so it's gonna be a fun 2 hours. I'm gonna maybe try and figure out how to not talk so much, but that's unlikely. I have to talk quieter. I've got a microphone here. I should practice talking quieter, but I'm not good at it. So we want to find, what we're going to do is we're actually going to set up an inequality. So if you look at this picture, this smaller sector, I teach a pre-16 class. Yeah, it's a good class too. It's definitely, but it definitely is, it's me talking all the time. So it shouldn't be. I should try to do more with the students do stuff, but that is something I need to work on. So just looking at this picture, we can hopefully kind of see here that I should have like, I wonder if I could like draw on this. Probably, I don't know, ooh, can I draw on this? Can we have fun? Maybe, probably not. I'm probably not very, can I draw? No, okay, let's not try that. So anyway, the area of this smaller sector, OCP, is smaller than the area of the triangle OCB, and that's smaller than the area of the larger sector OAB, which I've written right here. And then we have the formulas for these things. Triangle is easy, right? Triangle area is 1/2 base times height. It's pretty standard. The area of a sector is something that people, I feel like, tend to forget. The area of a sector is 1/2 r squared times theta. Now, I usually think about this in the context of a circle. What's the angle of an entire circle? I do see that, but so let me ask the question again. What's the angle of an entire circle in radians? If we go all the way around, how many radians is that?
It's 2, right?
Yeah, 2 pi.
2 pi radians.
Yeah, go away. So yeah, so the whole circle is 2 pi. So if I was going to use this formula to calculate the area of the entire sector, which is the circle, it'd be 1/2 times my radius squared times 2 pi. The 1/2 and the 2 cancel out, and you get r squared times pi, or pi r squared. So it seems totally reasonable, right? This would be the formula, right? That if that your angle basically gives you the fraction of the circle that you have. So if you have the whole circle, your angle is 2 pi. If you have half a circle, your angle is pi, and you get 1/2 times pi r squared, which is literally 1/2 the area of the circle. So I mean, you can look at this later. It's really just based on ratios, this formula for the area of a sector, but this is the formula for the area of a sector. So here's what we've got. I've got 1/2 times the small radius squared times the angle theta is less than or equal to 1/2 OC, which is the base of that triangle, times BC, which is the height of that triangle, which is less than or equal to 1/2 times the large radius OA quantity squared times the angle. And now we're going to make some substitutions. So first of all, we see up here that OC is equal to cosine theta. So I'm going to rewrite this as 1/2 cosine squared theta times theta. This inside part here, again, OC is cosine theta and BC is sine theta. So that the area of this, so that this middle part is 1/2 cosine theta times sine theta. And finally, this last right-hand part is even the easiest. OA is just equal to 1, right? We used a unit circle with a radius of 1. So this is just 1/2 times 1 squared times theta. Okay, here's the goal now. The goal is to use the squeeze theorem. The goal is to make the middle part look like the thing we're trying to take the limit of, which is sine theta over theta. So the way I'm going to make this middle part, which I would love to be more computer literate and like be able to like make little boxes and things, but I am not. So I can just point at it there with my pointer. Ooh, I can make it big by moving it around fast. There is my 1/2 cosine theta sine theta, and I want to make that sine theta over theta. So I'm going to multiply by 2 to get rid of the 1/2. I'm going to divide by cosine theta, and I'm going to divide by theta to have a theta under the sine theta, which is exactly what I'm doing here. I'm multiplying everything by 2 over theta cosine theta. So I did that for the first thing, for the middle thing, for the last thing. So in the middle, I exactly get what I was trying to get, sine theta over theta, right? The 2's cancel, the cosine thetas cancel, and I'm left with the sine theta on top and this theta over here on the bottom. On the left-hand part, the 2's cancel, the thetas cancel, and one of the cosine thetas cancels to give me just a cosine theta. And over here on the right-hand side, the 2's cancel, the thetas cancel, and I'm left with a cosine theta in the denominator. So now I've got a compound inequality. The thing I'm trying to take the limit of is in the middle. So what do? I take the limit of the parts on the outsides. So I take the limit as theta goes to 0 of cosine theta, which we can just plug in 0, and cosine of 0 is equal to 1. I take the limit as theta goes to 0 of 1 over cosine theta. I can do the same thing. Cosine of 0 is equal to 1, so I get 1 over 1, which is still 1. And so since the limit of this is equal to 1, and the limit of this is equal to 1, the limit of the middle part is equal to 1. And before I go to questions, let me do a couple things here because I just had a good idea. We can also see this on Desmos. But I need to stop sharing this. I'm just sharing this particular part of my screen. So let me start sharing again. Let me share now. Let's just share the whole thing. So yeah, Desmos, yeah, get to work, Desmos. So if we want to look at just cosine versus 1 over cosine, so here is y equal, I'm going to use x even though we use theta there, it doesn't really matter. Right. And then here is 1 over cosine. And we can definitely see that if there's something that's in between the red and the blue thing, as we get closer and closer to 0, it's going to get squeezed to 1. And if we go ahead and graph sine x over x, and then I have an interesting thing to tell you guys about Desmos. Oops, maybe I should try typing the things right. Come on, I didn't need that privacy over there. So there's sine x over x, which is totally, at least when we're getting close to 0, totally squeezed between cosine x and whatever cosine x. So it took a lot of work to make that inequality show up. But now that we see that we have that inequality, we can definitely see, oh yeah, Squeeze Theorem says that that's equal to 1. I just want to see here. Yeah. So I'm going to turn these, I'm going to delete these for a second. So something to be aware of with Desmos. Come on, I want the point there. Yes, okay. So right there, it says 0 undefined, which it is, right? And we can obviously see from the left and from the right that the limit is 1. But what my friend was telling me today, and I haven't tested this out, so I believe her because she is a smart person who knows things, but I haven't checked it. She told me that this might be an exception, but for a lot of the graphs on Desmos, they actually won't show you undefined points like that for things like 0, 0. For example, we talked about how this example, 9 minus x squared, divide, come on, James, be smarter about this. I want the 9, there we go, okay, there we go. Over 3 minus x. We know that this line should be undefined at x equal to 3. Because if you plug in 3, it's 0 over 0. However, if you look at the graph here, oh no, it does. So she was pointing out to me that apparently some graphs like this sometimes don't actually say it's undefined there. So just as a word of warning, you should be careful, right? We obviously know it's undefined, and here it is showing as undefined. But she was telling me she was reading about how some of these things where you would expect it to be undefined at a point like that are not. Now I'm curious, let's do one more. Let's do 1 minus cosine of x, because this is another one that comes up a lot, all divided by x. If we go back and check that one out. So again, this one is definitely undefined at 0, although we can certainly see that it approaches 0 as x approaches 0. If we try clicking on the point there, no, it shows it's undefined. I'll have to ask her to show me some examples, because again, I don't think she was lying to me or wrong. I just think I'm not coming up with the right examples. But be wary of using Desmos to find out what your limits are, or if things are continuous, right? Because apparently there might be some small issues around places where things have an undefined place. All right, so we looked at some fun pictures, and I'll remind you, so we can definitely see, and we did see the proof that the limit as x goes to 0, sine x over x is definitely equal to 1. And you can also see from this picture that the limit as x goes to 0 of 1 minus cosine x over x is equal to 0, because as we get closer and closer to 0 for the x values, the y values also get closer and closer to 0 from either side. So the right-hand limit is 0 and the left-hand limit is 0. We'll also talk about one-sided limits today. All right, I think that's all the screen sharing I need to do for the moment. I might come back and share a screen with another thing though. That's a great picture, I love that. Let me pin my own video though here. Great, okay, there's me. So quite a few things to talk about today. And we're gonna start with these trig limits where you've got like sine x over x stuff. And, ooh, sorry, let me do one other thing. One moment, please. Sorry, I just need to pull up some. Yeah, there we go. I've got lots of examples of this, but I want to make sure I have extra examples just in case. Sure. There we go. That's the page I was looking for. All right. So let's get going. Here's my pen. There's my pen. And I got lots of pens, but here's the one I want. So the big thing to remember is that the limit as something goes to 0 of sine of that something over the same something is equal to 1. And there's a lot of different ways this can be used. For example, this thing here doesn't have to be exactly the same as those things there. I could also say the limit as theta goes to 0 of sine of 3 theta over 3 theta is equal to 1. Basically, the thing that I think is kind of the important point is to remember that you basically have, for the limit to equal 1, you have to have sine of some stuff over the exact same stuff, and the stuff has to be approaching 0. So the way I typically write it is I need the limit of sine of some stuff over the exact same stuff as the stuff is going to 0. And here we have that, right? I've got sine of some stuff for the same stuff. And since theta is going to 0, 3 times theta is also going to 0. So I have sine of a thing over the same exact thing, and both of those things are going to 0. As a counter example, what if I had sine as x approaches 0 of, sorry, oh my gosh, that, well, first of all, there is an idiotic thing to write. Sorry about that. Sine as x approaches 0. Okay, good job. How about the limit as x approaches 0 of, what do I want right here? Sine of pi x over 2 over pi x over 2. Oh, that's a terrible example, James. How about trying this instead? Sorry, I thought I had a good one in my head, but I didn't. How about this? How about pi over 3 plus x? Yeah, that'll work. Over pi over 3 plus x. Okay. It would be very easy to make the mistake of saying this was equal to 1, because it kind of looks like it has the right format, right? You've got sine, you've got the limit as x goes to 0 of sine of a thing over the same thing. The problem here is that the things aren't going to 0. X is going to 0. Here the things are going to pi over 3. In fact, this is an example of someone trying to trick you. They're trying to make you say it's 1, but really it's like, I'm going to plug it in, because you should always, if you're faced with a limit, maybe not write it out, but at least try thinking about, okay, if I plugged in x equal to 0 or whatever x is approaching, do I get a real number? If I do, great, I'm done. And we do here. We get sine of pi over 3 over pi over 3. Right? There's no issues there. I mean, the issue is we have to evaluate sine of pi over 3, which is root 3 over 2 divided by pi over 3. But that's a real answer, right? It's a real not nice number. And then you could rationalize it if you really wanted to. So you get 3 root 3 over 2 pi. So there's an example of people trying to be a little bit tricky. Here's another example. This one's more tricky. The limit as x approaches 0 of sine of 1 over x over 1 over x. Again, this looks like it could have a limit that's equal to 1. It doesn't. Because although 1 over x and 1 over x are the same, right? I've got sine of a thing over the same thing. The limit as x goes to 0, the stuff isn't going to 0, right? If x is going to 0, 1 over x is going about as far away from 0 as it can, right? It's getting infinitely large or negatively infinitely large, depending on the side of 0 you're approaching from. So instead, this problem, you have to approach totally differently. In fact, we kind of have a clue. So let me see a thing here. Let me change the video thing here. But so I'm going to give you a clue for that problem while I'm doing this, which is that you have sine of something going to infinity. When we have sine of something going to infinity, what do we often have to use? We have to use the squeeze theorem here. It is a little bit easier if you rewrite it as the limit as x goes to 0 of x times sine of 1 over x. That makes it a little more obvious that, oh, we know that, do I have enough room here? Maybe. Sure. We know that sine of anything is always between 1 and -1. So I can multiply all sides by x and say that negative x is less than or equal to x times sine of 1 over x is less than or equal to x. And then I can take the limit of both the left end and the right end as x goes to 0. And the limit as x goes to 0 of x is 0. And so is the limit as x goes to 0 of negative x. 0. So since the limit of this is 0 and the limit of this is 0, the limit of the inside parts has to equal 0 by the squeeze theorem. So this limit is actually 0 by the squeeze theorem. So what I'm trying to emphasize here is don't let yourself get fooled, right? To say that this type of limit is equal to 1, you have to have sine of a thing over the same exact thing. And additionally, the things have to both be getting closer and closer to 0. They can't be getting closer and closer to pi over 3. They can't be getting infinitely large. 0 is the only place they're allowed to be getting closer and closer to. All right. With that in mind, let's look at some examples. Like this limit. The limit as x goes to 0 of sine of 4x over 7x. And here I've mostly got what I need. I've got that both sine of 7x and 4x, I should say, both 4x and 7x are going to 0. So I've got a sine of 0 over 0. The issue here is the other thing. It's not that they're not going to 0, it's that they're not the same. Right? I really wish I had sine of 4x over 4x. And so that's what I'm going to do. This is actually what I call the wish method, is I'm going to write down what I wish I had. Well, I'm going to do that in a second. I'm going to do one other thing first, which is I'm going to write down what I have. So I have sine of 4x over 7x. I like to write it that way. So basically, each piece of my fraction or each factor kind of gets its own fraction. And then I'm literally going to ask myself the question, what do I wish was going with sine of 4x? So what do I wish was in the denominator here? And the answer is 4x. I wish I had a 4x there. Well, great. I can put one there as long as I balance it out. Essentially multiplying by 4x over 4x. Okay, so then we can do a couple things. And this really kind of depends on how much work your teacher wants you to do. We can write this as, so 4x over 7x, this is just equal to 4/7. Wow, that 7 does not look good. Right, because the x's can cancel there. So I can write this as the limit as x goes to 0 of 4/7 times sine of 4x over 4x. But this part just goes to 1. So this is equal to 4/7 times 1, which is 4/7. That's it. So why don't you guys try this one? Try finding the limit as x goes to 0 of sine of 6x over 4x. And I'll give you a minute. I need like a stopwatch in here. Maybe I have one. I'll give myself a minute to find a stopwatch. So hopefully everyone is getting 3/2 or 1.5 is their answer. But let me show the work. This is not the only way to do it, by the way. This is just the way I think works best. So I'm going to say this is the limit as x goes to 0 of sine of 6x over blank times blank over 4x. So I haven't changed anything yet. And then I wish I had a 6x down there. And then I'm going to write a 6x up there too, just for it. I should point out, we're always trying to match whatever is in the sine function. Right? I don't want to put like a sine of 4x over here and a sine of 4x down there. That would make things more complicated. I want to try and make this easier. So then usually the work that I really show is I cancel the x's and I say that this part is going to have a limit that's equal to 1. So I'm going to get 1 times 6/4, which reduces to 3/2. And that's my answer. Excuse me. I also wanted to mention, just in case, I imagine most of you know this, but maybe not everyone knows it, you can type in the chat privately to me if you have a question that you don't want your classmates to see. That is always an option. I know I definitely was the kind of person in class that I didn't maybe want to ask my question in front of everybody. So if that is you, that is perfectly fine. You can also just type your question in the chat if you don't care, right? Either way, perfectly fine. So these, of course, do get a bit more complicated. And there's a couple of different things to cover here. One of them is, let me see what I wrote down here. Yeah, okay, there's all that stuff, cool. So one of them is something, there's like 4 different varieties. So let's talk about them all. So what if I have, say, the limit as x goes to 0 of, say, tangent of 3x over 2x, or, and we'll do this one next, the limit as x goes to 0 of, that's actually interesting. I could do that, sure. We'll do, yeah, that'll be fun. Tangent of 5x over sine of 4x. What's interesting about a lot of these problems, not all of them, if you've got squares and stuff, it's not always true. But for these kind of ones where you just have tangent or sine to a first power, you almost always get an answer that's just the ratio of these numbers. So looking at this, I know the answer is going to be 3/2, and the answer is going to be 5/4. There are more complicated ones where we actually have to do the work to be able to see it. But here, we can kind of see it right now. Tangent isn't sine, but it acts a lot like sine. Because what we can really do for tangent is rewrite tangent of an angle as sine over that angle, sine of that angle over the same cosine of that angle. So I can write this as sine of 3x over cosine of 3x times 1 over 2x. Right, that's how I really prefer to write it. Instead of that divided by 2x, let's just write it as nice all fractions. And then I'm going to break it up into 3 separate fractions, just because that's going to work for me. Right, this is the limit as x goes to 0 of sine of 3x over blank times blank over cosine of 3x times, I'll just write that as a blank over 2x for a minute. Maybe I'll fill in the 1. So there's all the factors I have. The only one that matters, the only one that I really have to be careful about, is the sine of 3x. What do I wish was in the denominator of that sine of 3x fraction?
3x.
Exactly. Okay, now once I put something in the bottom, I have to adjust by putting the same thing in the numerator. Or I really should say, once I divide by a thing, I also have to multiply by it, so I'm not changing the value. Now, I could put the 3x over here, but that's not super helpful. I'm going to put the 3x here, where I can actually cancel out the x's. And then I've pretty much done all I need to do, because here's the thing, cosine doesn't matter. Not that cosine doesn't matter, but sine of 0 is challenging because you end up getting 0. Cosine of 0 is not a problem in the denominator, because cosine of 0 is equal to 1. So dividing by cosine isn't something that we really need to be concerned about in these sorts of limit expressions. So I'm just going to say I've got a 1 up there, and then here's what I get. This part goes to 1. This part also goes to 1 or 1 over 1. And this part goes to 3 halves. So my answer would be 1 times 1 times 3 halves, which is 3 halves. Something to be careful about, which I know people often kind of get confused about. I want to really make the point clear. I'm not saying that sine of 3x over 3x is equal to 1. I'm saying that the limit as x goes to 0 of sine of 3x over 3x is going to equal 1. So it's really, I've definitely, you should never write this down. This is actually never true. The limit is equal to 1, but this expression is never equal to 1. It's certainly not always equal to 1, but it's in fact never equal to 1, which is interesting. Okay. Before we do this one, I feel like there's something else we have to address. So I'm going to start this problem, and then I'm going to come, and then we'll flip, and then we'll come back. So I'm going to break this one apart into sines and cosines as well. So this is the limit as x goes to 0. Tangent to 5x, I'm going to write as sine of 5x over cosine of 5x. But I really want to break them apart. And then divided by sine of 4x is like multiplying by 1 over sine of 4x. Except I want to leave off the 1 because I might want to fill it in with something. But I might need more space for this. We'll see. Yeah, I feel like, I feel like maybe I picked a bad problem. Let's find out. Well, this might work out fine. This might just be funky. So, yeah. So sometimes you need an extra fraction space, which I guess I'll have to put in front because I left myself non-nothing at the end. Okay. So before we can do this, let me do something else. So we'll come back. Leave yourself a little bit of space. But particularly, we have to talk about sine x over sine x. So what I want to eventually say is that for this something over sine of 4x, I want a 4x up there. But I kind of have to justify that. So here's what I want to point out. Ooh, and here's a good segue into some limit rules. So I want to take the limit as x goes to 0 of x over sine of x. So here's what we're going to do. We're going to write this as the limit as x goes to 0 of 1 over the reciprocal, sine x over x. Normally what I would do is just say the limit of this is 1 over the limit of that. But I'm actually going to show you what we would do with some of the limit rules, which we'll then do another example of a little bit. So when you have, so really we don't use these rules, and we also use them all the time, meaning we use them without saying we're using them. So normally I would jump straight to here. I would do the work I'm going to do and then say, okay, this is equal to the limit as x goes to 0 of 1 over, sorry, that's not what I actually meant to write. I would say it's 1 over the limit as x goes to 0 of sine x over x. And then say, oh, I know that that limit's 1, so it's 1 over 1, which is 1. And normally that would be a perfectly sufficient amount of work to show. But what I've actually done is I've used at least 2 of the limit rules in this process. The first rule I'm using is that if you have the limit of a quotient, it's equal to the quotient of the limits, meaning it's equal to the limit as x goes to 0 of 1 over the limit as x goes to 0 of sine x over x. And then the second rule I used was that the limit of a constant is just the constant. So the limit as x goes to 0 of 1 is just 1. So those are the 2 limit rules I use. But again, most of the time, we don't actually explicitly write out that we use those rules. We just say, well, we all know how those rules work, or we pretend like we all know how. I mean, it's not that we pretend. It's just that we we don't require so much exposition of these rules because it gets real super tedious. So we say, okay, yeah, we know how the fractions work, we know how the constants work, and we just jump straight to here. Like, yeah. And so what this means for us is that if you have the limit as x goes to 0 of sine x over x, you get 1. And it's also true that the reciprocal has a limit that's 1. So we can more generally say that the limit as some stuff goes to 0 of some stuff over sine of your stuff is also equal to 1. So what that means, going back to the previous problem, is that, well, for sure, we know we want a 5, we wish we had a 5x down here, so that the limit of this part's 1. But if we have a 5x down here, we need a 5x up here to balance it out. We also wish we had a 4x up here, so that the limit of this part is also 1, because again, it's a thing over sine of the same thing, and the thing is going to 0. If I have a 4x down up here, I need to put a 4x in the denominator to balance it out. And then finally, I just need a 1 up here. So then these x's cancel, and I end up with, now really I could point out that I'm using, in fact, yeah, I am going to point out, I am taking a shortcut in this last step. I'm just going to say, well, I'm actually going to show you the steps I'm doing. But the shortcut I would usually take would be to say, my answer is 5/4 times 1 times 1 over cosine of 0, which is 1, times 1. But what you could actually write using the product rule for limits is that the limit of all these products is the product of all the limits. So this is equal to, actually I'm going to do the convolution. So the 5/4, you can bring a constant multiple out in front and say it's equal to 5/4 times the limit of the first part times the limit of the second part times the limit of the third part. Nobody really wants you to write out all these steps unless they ask you to specifically. Like usually there's like 1 or 2 homework problems, or maybe a few more, or they're like, here's a limit. Use the limit rules to show what this limit's equal to. But most of the time they're just like, no, don't do that. So then we're going to get 5/4 times the limit of this is 1. The limit of this is 1 just because if you plug in 0, you get 1 over 1. And the limit of this is 1. So my final answer is 5/4. I should point out that these limit rules are only true if each of the individual limits exist, right? You can only say that the limit of a product is equal to the product of the limits if each of those individual limits exist and this whole limit exists in the first place. So just a point of clarification there.
So sine of 0 is 0?
Correct.
Then how does it make it cancel out to make 1?
So it's not that they're canceling it. So maybe you weren't here at the very beginning of class, Helena, but we definitely talked about how generally, if you have the limit as some stuff goes to 0 of sine of stuff over the same stuff, that limit is equal to 1. And so that's the rule that we're using here. And if you look at the co-class modules, there's a module that has useful handouts that has a proof of this fact. But that's what we're using here. We're saying, oh, I've got sine of a thing over the same thing. As long as that stuff is going to 0, which it is, if x is going to 0, 5x is going to 0, then that limit is going to equal 1. And the same thing is true here. If you have the reciprocal, it's also going to be 1. And that makes sense because the reciprocal of 1 is still 1. So that's what's going on there. I think you can move this a little bit this way. Yeah, that's a little bit better. Let's see. I know there was a couple other versions of this I wanted to mention. Let's see. sure. Yeah. So hopefully that kind of clarifies your question a little bit.
Yeah, thank you.
Well, I've got a few more varieties of this, and then we'll take a break, I think. Which way do I want to go here? Yeah, let's go with that. So another very popular limit. So there's a reason we talk about these limits actually, specifically sine x over x and 1 minus cosine x over x. And it's really because they actually come up in the limit definition of the derivative for sine and for cosine. So that's why these limits are especially important. So you'll definitely see, or you'll probably definitely see later on when we talk about the derivative of sine and cosine, that the limit as h goes to 0 of sine of h over h is equal to 1. And the limit as h goes to 0 of 1 minus cosine h over h is equal to 0. So we're going to do that now. So we're going to use x's. So this limit is 0. And the way we show it's 0 is by using a trick. The trick here is to get it to be sine x over x somehow. And so what we're going to do is we're going to multiply by the conjugate. And I will say more generally, if you ever see 1 plus cosine or 1 minus cosine, or 1 plus sine or 1 minus sine, multiplying by the conjugate is often a good trick because it will always make a trig identity come out. So in this case, here's what we get. Limit as x goes to 0. 1 minus cosine times 1 plus cosine is 1 minus cosine squared x. And the denominator I'm just going to leave as x times 1 plus cosine x. All right. So now, 1 minus cosine squared x, the trig identity for that is sine squared x. This is equal to the limit as x goes to 0 of sine squared x over x times 1 plus cosine x. And then here's where we have to be kind of extra inventive, maybe. You want to break this fraction up into product or factors where you've got pieces that you want. One piece I'm always trying to get is sine x over x. So I can rewrite this limit. Also, do make sure you're writing the limit in each step. I'm right at the top as sine x times sine x. The bottom is still x times 1 plus cosine x. And I probably could have done this in the same step. But then I really want to break it apart as sine x over x times sine x over 1 plus cosine x. Okay, let me ask you guys. As x goes to 0, what's the limit of sine x over x? This is not meant to be a hard question. Yeah, exactly. That's definitely 1. Okay, here's a maybe harder question just because we're not used to it. As x goes to 0, what's the limit as what's the limit as x goes to 0 of sine x over 1 plus cosine x? Well, we can just plug it in. Sine of 0 is 0. Cosine of 0 is 1. So I end up with 1 times 0 divided by 2. 0 divided by 2 is just 0. 1 times 0 is just 0. So this ends up being 0. Let's ask a more interesting question. Let's see, what have I got here? Yeah, that's fine. We can do either one of these. So we can look at either this, as x goes to 0, 1 minus cosine x over x squared, or the limit as x goes to 0. Is that what I really want? Yeah, I guess so. Yeah, that's what I want. I've decided. feel like someone asked me a different question. No, yeah, that's fine. I guess that's reasonable, sure. But I think someone asked me this question. We can also look at 1 minus cosine x over sine x. And so this one might be weird. I don't know. We'll see. For either one of these, I'm still going to use the conjugate because that's really where my brain goes. Like, I don't know what else to do other than try using the conjugate here. So I'm going to multiply this by, I'm going to do the bottom one first just because I want to. All right, so let's say I get the limit as x goes to 0. Again, when you multiply 1 minus cosine times 1 plus cosine, you get 1 minus cosine squared. And I will say this is usually true when you're multiplying something, when you're like simplifying something or trying to change something by multiplying by a conjugate, you almost always want to multiply out the things that are actually conjugates, and you don't want to multiply out the things that are not conjugates. So you want to leave the denominator as sine of x times 1 plus cosine x. You don't want to distribute that and write sine x plus sine x times cosine x, because we're probably trying to cancel that sign. So then we have the limit as x goes to 0. The whole point of multiplying by the conjugate of 1 minus cosine, so the top part would become the trig identity equal to sine squared. So the limit as x goes to 0 of sine squared x over sine of x times 1 plus cosine of x. Yeah, we're going to have a problem here. It's okay. It's not too terrible. And then I can cancel one of those signs. Well, maybe we don't have a problem. I'm a liar. We don't have a problem. I was imagining some other kind of weird problem. So then the limit as x goes to 0 of sine of x over 1 plus cosine of x. And I want to point out, I canceled the thing in the denominator that was making the denominator equal to 0. After you have done that, wherever you are in your limit taking, it is usually a good idea to reevaluate and see if you can just plug things in. So typically, after canceling something, it's usually good to check to see, can I just throw whatever x is approaching into the thing and see if I get an answer? And we do here. I get sine of 0 over 1 plus cosine of 0. Sine of 0 is 0. Cosine of 0 is 1. And 0 divided by anything that's not 0 is 0, right? 2 goes into 0, 0 times. So this limit's 0. So this problem, actually I don't know what it's supposed to be. Let's figure it out. I think it's gonna be 1/2. Oh, actually, let me see, I can check. Yeah, it's gonna be, it's gonna be either 1/2 or negative 1/2. So we're gonna do the same thing, right? We're gonna multiply by the conjugate. Multiply 1 plus cosine x, 1 plus cosine x. So I feel like we've done this enough times now that we know that 1 minus cosine times 1 plus cosine is going to be 1 minus cosine squared, which is equal to sine squared. So let's cut to the chase. And see, this is the limit as x goes to 0 of sine squared x over x squared times 1 plus cosine x. And now here's how I'm going to write this. I could write it as sine squared over x squared, but I feel like that's not quite explicit enough for me to see that what I've really got here, I've got a sine x over x. I've got another sine x over x. And then I've got a 1 over 1 plus cosine of x. Right? And this is the same. So we multiply this all out. The top is sine x times 1, which is sine squared. And the bottom is x times 1 plus cosine x, which is x squared times 1 plus cosine x. So I'm just breaking this up into factors that are convenient to deal with, right? The factors, the pieces that I want. So the limit of this is 1, the limit of this is 1, and the limit of this is 1 over 1 plus cosine of 0, which is 1. So 1 over 1 plus 1 is 1/2. So I end up with 1 times 1 times 1/2, which is 1/2. So that's how you approach one like this. Okay, there's just one more variety of this kind of question that I want to address real quickly, and then we'll move on to I was going to talk about continuity, and actually probably do a, there was something else. Oh yeah, I was going to talk about limit laws and continuity, and maybe one more delta epsilon example. Oh, I know what I want to say. Also, I did post solutions to the quiz that I gave you guys on Canvas. So if you're curious about how many of those problems need to have been done, those are on there. They might not be up as fast in the future, but I had time to write them up today, so I did. I will try to post solutions to them in general. These ones are nicely typed. They might be handwritten in the future because it's usually faster to handwrite something. But let me see. I want to. So let's look at one like this. Limit as x goes to 0, sine squared of 3x over 4x squared. And here's what I want to warn you against. This limit is not going to end up being 3/4, right? Our other examples have been, like we just take the coefficients and it works out nicely, but that's not what we have here. So this is really where I think breaking it up into the component pieces is very, very useful. So I'm going to write this as the limit as x goes to 0. Sine squared of 3x is sine of 3x times sine of 3x. And then divided by 4x squared is the same as multiplying by 1 over 4x squared. So that's the way I really want to write it. I find it very, very convenient to do so. And then just like a few problems before, what do I wish was beneath sine of 3x? A 3x. What do I wish was beneath sine of 3x? A 3x. But then I need to balance those 3x's in the denominator with 3x's in the numerator. So then this ends up equaling 1 times the x's cancel, and I get 3 times 3 over 4, which ends up being 9/4. Sometimes teachers ask questions like this after you've learned L'Hopital's rule, and using L'Hopital's rule for this is terrible. This one's not super terrible, but it's really, really, there are some problems where although you totally could use L'Hopital's rule here. If you haven't heard L'Hopital's rule, don't worry about it. We'll cover it before the end of the quarter. But even though you could use L'Hopital's rule sometimes it is an awful choice to do so. And this is an example of a question where it is an awful choice to use L'Hopital's rule. Here's another example that's even worse. Again, I know we haven't officially learned L'Hopital's rule yet, so I'm not going to actually try using it. I just want to point out that if you know it and you try to use it for this problem or the next problem, it's really a bad choice. So limit as x goes to 0. Let's do sine cubed of 5x over 8x cubed. So actually, I want you guys to try this one. I want you to write it into 4 different fractions multiplied together. Sine of 5x times sine of 5x times sine of 5x times 1 over 8x cubed. And then try and make it look like what you want it to look like so that it comes out to be relatively easy to deal with. And I'll give you 2 minutes, and I've got my watch now that I can look at. I'll give you 1.5 minutes. think it's been about a minute and a half. And I think you should end up with 125 over 8 here. But let's have a sine of 5x times the sine of 5. My 5's never worked good. Those are like S's. 5x times the sine of 5x sine blank over 8x cubed. All right. So I'm going to put a 5x here, a 5x here, a 5x here. And here's a mistake I've seen people make on occasion. I see people will write 5x cubed, which isn't correct. It's correct if you write 5x quantity cubed, but I would personally just make the choice to write 5x times 5x times 5x. That just is a more sure way of not making an error. And then, of course, again, right, this thing here, which is sine of something over the same something, and the somethings are going to 0, that limit is 1, and 1, and 1, times 5 times something 5 over 8, because the x's all cancel out. You get 125 over 8. All right, so that is most of how these limits with sine x over x kind of work out. I mean, there's probably some other flavors that you could introduce, but that is a big picture, a lot of what you're going to see. So let's move on. I know someone asked to see one more precise definition of a limit example, so I think I'll do one more just to kind of remind you guys again of what that looks like. Okay, so the question I guess I should really ask is, do you guys want to see another linear example, or do you want to see a non-linear example of a precise definition of a limit?
Non-linear.
Okay, yeah, I figured that's what you guys were going to say. I'm going to have to come up with one. I can do that. I can do that. Let's do that. That should be sure. Let's prove that the limit as x approaches 8 of the cube root of. I was going to do that, but that seems boring. Let's do. Let's do that. I feel like we can make that more interesting, but we don't have to. So let's just stick with this. Okay, so again, we're trying to do this. Our job is to make two things be true at the same time. So here's what we want to be true. We want both the absolute value of x minus 8 to be less than delta, and the opposite value of the cube root of x minus 2 to be less than epsilon. And my brain always thinks of these a little bit differently than I feel like the book actually does, or maybe my friend, my coworker. Basically, the idea is that for each of these, we have to isolate x in the middle of a compound inequality. So this one is easy, relatively speaking. You got x minus 8 is less than, we usually do like, I used to say this is delta 2, and I feel like this is like negative delta 1 is what we're really saying there. And that's what we usually end up having. And then you got x is less than 8 plus delta 2, bigger than 8 minus delta 1. And so if we're looking at the picture of things, I guess I could try drawing down here. Sure, I can draw sometimes. If we're over here, right, here's our function. If we're over here, here's 8. Let me be smart about this. Sure. Here's 8 minus delta 1, and here's 8 plus delta 2. So that this distance here is your delta 2. This distance here is your delta 1. And our job for these kinds of non-linear examples is to figure out which of those deltas is the smaller value, right? That's the value we want. We want to pick delta to be the minimum of delta 1 and delta 2. And I think my picture is actually, I forget. I feel like it's steeper to the left. So the smaller delta 1 should be the one that's to the left, because the smaller delta should be the part of the graph where the graph is steeper. So I feel like I kind of drawn my picture so it doesn't super accurately reflect what we're going to get, but that's what should happen. So let me do the same thing on the right, which is usually, or for the epsilon part, which is usually going to be a little bit weirder looking. So again, we got the cube. We're going to break this absolute value up into being like this. Where you get your stuff in the middle, less than epsilon, bigger than negative epsilon. And then, right, we don't do epsilon and epsilon 2 because the epsilons are the same, right? This is epsilon, this is epsilon. So that number there is 2 plus epsilon. That number there is 2 minus epsilon. So we're going to add 2 to both sides. And then we're going to cube both sides. So x is between epsilon plus 2 cubed and 2 minus epsilon cubed. All right. And then we do the thing where we set these things equal to those things, which always feels funky. All right. So I'm going to go to the other side. And again, I am personally expecting the delta 1 to be the smaller value because it comes from the graph, the part of the graph that is steeper. Right? That is usually that is always the thing that should be true. Because if it's the steeper part of the graph, you get more change in y for less change in x. So I already found this right then. So we're setting this equal to that. So 8 minus delta 1 equals 2 minus epsilon cubed. And we're setting, where'd you get this equal to that? So 8 plus delta 2 equals delta 1. And we're trying to solve for delta here. Okay, so that's not too hard. Here, right, delta 2 is going to equal epsilon plus 2 cubed minus 8, which you could totally simplify if you wanted to, right? You could multiply it. I don't know if that's really necessary, but this is epsilon cubed plus 3 epsilon squared times 2, so 6 epsilon squared plus 3 times epsilon. Sorry, it's been a while. 3 12 epsilon plus 8 minus 8. So there's your delta 2. And your delta 1, so solving for delta 1, I'm going to have delta 1 equals 8 minus this. And 2 minus epsilon cubed is 8 minus 12 epsilon squared plus 6 epsilon minus epsilon cubed. So delta 1 ends up being epsilon cubed minus 6 epsilon plus 12 epsilon squared. All right. So now the question, which of these is smaller? I'm pretty sure it's this one. And again, I would just check by plugging in a number like 1. You don't want to go too big, otherwise you get weird stuff happening. But it certainly seems reasonable to go up 1 and down 1 and still be in a not weird part of the graph. So I plug in 1. I plug in 1. Delta 1 is going to be 1 minus 6 plus 12, which is 7. I plug in 1 here, and you get 1 plus 6 plus 12, which is 19. So delta 1 appears to be the smaller choice. You could probably, I mean, I don't think you should at all, but you could actually say, like, set this to be less than that, and then figure out what your restriction on epsilon actually is. But I don't really feel like that's the point of the problem, so I don't think we should do that. But yeah, you could totally, yeah, I mean, I really want to do it, but you shouldn't. So yeah, anyway. So then we have to go write the proof, which is always the part that feels especially funky for these nonlinear ones. So here's my delta 1. Yeah. Which you might leave as 8 minus 2 minus epsilon cubed. I don't know. So where to write the thing? We want this to be true. Okay, so I have to erase somewhere. It's got to be here, I guess. The proof for these nonlinear ones feels less wordy because there's really so much less. Now you would probably have all that work showing above. And then we write our proof. So we see that for any epsilon greater than 0, if the opposite value of x minus 2 is less than our delta 1, which I'm actually going to write. Wow, that's a really good delta. That's not much better. Try one more time. Yeah, that's a little better. Which we found to be this quantity here, 8 minus 2 minus epsilon cubed. I do kind of feel like that's the better way to write it. Then we get that our function, I made a mistake. It's okay, I can fix it. It's not like a big mistake, it's a mistake in my proof, right? What should this actually be here?
8, x minus 8.
Yeah. Then our function, cube root of x minus 2 is less than epsilon. And we know that that's true because of the algebra work we just did. So typically for these nonlinear proofs, you don't do any kind of rewriting of all the algebraic computation you just did. You kind of reference it and you kind of say, like, there's the work up here, and then here's my proof down here. Thus, the limit as x approaches 8 of the cube root, sorry, I started writing opposite value for some reason, of the cube root of x is equal to 2. That's how we would prove it.
Do we need to write that epsilon is greater than 0?
We usually, I mean, it is true that epsilon needs to be positive.
I think it's always, you have to write let epsilon be greater than 0. That's the first step. Yeah.
Oh, yes, and which I've essentially included right here.
Yeah.
But yeah, often people start off with let epsilon be greater than 0, then proof. I kind of just caught it right there. But yeah, you may, yes, we do need to write that is the answer to your question in one way or another. Okay, I think we should do one thing and then we should do another thing. Very specific, I know. So I want to talk about continuity, but before I talk about continuity, I do want to just say one thing about the limit rules. So there's a bunch of limit rules or limit laws that your teacher will probably show you at some point. And they're basically about how, like, the limit of a sum is the sum of the limits, the limit of a product is the product of the limits. Same is true for subtraction, addition, whatever. So here are kind of the very, very basic rules written extremely quickly. The limit as x approaches a of f plus or minus g is the limit as x approaches a of f plus or minus the limit as x approaches a of g. So basically the limit of the sum is the sum of the limits, or the limit of the difference is the difference of the limits. You don't have to copy these all down. I'm just writing them so that we have talked about them because there's something I want to say. We have a product, a limit of a product is equal to the product of the limits. We definitely used that a little bit earlier today. And then we also have the same rules true for division. The exception being if the denominator has a limit that's 0. This is not true if the denominator has a limit that's 0. Right, so again, all these limits have to exist for these statements to be true. And there's a couple more rules. If you have a limit as x approaches a of a constant times f, you can pull that constant out in front. Say it's the constant times limit as x approaches a of f. And then the limit of a constant is equal to the constant. The limit as x approaches a of a constant is equal to a constant. A couple more rules. Just two really that I want to say. The limit as x approaches a of x is equal to a, basically meaning you can plug in a for x and get a. And the limit as x approaches a of x to a power is a to that power. This is not an exhaustive list. There's kind of a few other things, but basically the idea is things work the way we think they work. Is a very generalistic way of saying it. Here's what I mean by this. So let's say I wanted to find the limit as x approaches 3 of, I don't know, 2x squared plus 5x minus 9 over 4x plus 7. I could use these limit rules, and I'm going to find this limit. But then I'm going to talk about how that's not what we ever really do. So the first limit rule I would use is that the limit of a quotient is the quotient of the limits. So I write this as the limit as x approaches 3 of 2x squared plus 5x minus 9 over, over the limit as x approaches 3 of 4x plus 7. Then in both the numerator and the denominator, I would use the rule that the limit of the sum or difference is equal to the sum or difference of the limits. So I write the top part as the limit as x approaches 3 of this plus the limit of this plus the limit of that. So the limit as x goes to 3 of 2x squared plus the limit as x goes to 3 of 5x minus the limit as x goes to 3 of 9 over, same rule here, limit as x goes to 3 of 4x plus the limit as x goes to 3 of 7. Okay. I don't have a rule yet for plugging this in here, so I have to actually pull this constant out as well. So the limit as x goes to 3 of 2x squared is 2 times the limit as x goes to 3 of x squared. And then I can pull out that 5 in front. That's plus 5 times the limit as x goes to 3 of x. Now the limit of a constant we know is the constant. So the limit as x goes to 3 of 9 is just a minus 9 there. On the bottom, I can factor out that 4, and I get 4 times the limit as x goes to 3 of x, plus the limit of a constant, again, is the constant. So the limit of 7 is just 7. And then I can finally use those last couple rules and say, okay, if we have the limit as x goes to 3 of x squared, I just get to plug in the 3 and say that that's 3 squared. So I get 2 times 3 squared. Same thing here. Limit as x goes to 3 of x is just whatever x is approaching, which is 3. So I get 5 times 3 minus 9 all over. Limit as x goes to 3 of x is just 3. So I get 4 times 3. And then we can do the arithmetic and get 2 times 9 is 18 plus 15 is 30. Well, let's just write it out. 18 plus 15 minus 9. Sorry, that looks terrible. Over 12 plus 9, which is going to be 33 minus 9 is 24 over 21, which reduces to 8 over 7. And unless you are specifically asked to, you should never, ever, ever do all this work to find the limit. Oh, did I make a mistake? 12 plus 7, not 12 plus 9. You might be right. Totally, yeah, thank you. Good catch. Sorry about that. So this won't reduce. We would have caught it in a second because I was going to do it the other way. But yeah, that should be a 12 plus 7 on the bottom. Thank you. And so I ended up getting 24 over 19. Yeah, good catch. Thank you. But you shouldn't do all that. That's a giant pain in the butt. What you should do is that if you're trying to evaluate the limit, you should just see, can I plug in 3 and get an answer? And we can. The same answer. If I plug in 3, I get 2 times 3 squared plus 5 times 3 minus 9 over 4 times 3 plus 7. And that ends up being exactly the same thing, 24 over 19. The point here is that all these limit rules allow us to do this, right? When we're plugging in 3, you're really saying, well, what I'm really doing is I'm breaking it this way and then this way, and then pulling the constants out, and then plugging it in and seeing that I get all the things coming back. But you don't have to show that work really ever unless someone specifically asks you to do so. So usually when we evaluate limits, we just ask, okay, can I plug in the number and get an answer? If the answer is yes, that is almost always your limit, unless someone has specifically tried to write a problem that is not the case for. But for any regular function, that is true. In fact, what I should really say is for any continuous function, it is always true that if you have a limit as x approaches something, you can just plug that number in or use what's called the direct substitution property and say that so the direct substitution property is what I just used, is that the limit as x approaches a of f of x is equal to f of a. And this property is true for, I'm going to say continuous functions, but I'm actually going to make it a little bit smaller, a little bit larger than that. It's true for continuous functions. And more generally, functions that are continuous on their domains. So functions that are rational functions, so including rational. So like actually the example we just did before, this function here, this function is not continuous everywhere. It is specifically discontinuous at -7/4 because it doesn't exist there. But it is a function that is continuous on its domain, meaning everywhere it's defined, it is a continuous function. And the type of discontinuity this has is typically a vertical asymptote. And I'll say more about that in a minute. So rational functions where you have a polynomial over polynomial. All trig functions are continuous on their domains. Tangent is continuous on this domain, right? Tangent looks like, why would I graph a thing when I have Desmos? That's a bad precedent to set. I can totally graph this faster than I can show it to Desmos. So here's what tangent looks like. Right? It's not defined at pi over 2 and 3 pi over 2 and negative pi over 2 and 5 pi over 2 and any odd multiple of pi over 2. But everywhere in between those pi over 2's, right, this is totally continuous. Totally continuous. Totally continuous. So trig functions, exponential, and log functions. Right? Log especially, a log function only defined for x greater than 0, but is totally continuous on that domain. So any of these functions, if you were asked about a limit of them, you can say, I'm just going to plug in whatever x is approaching, and that will give me the limit back. So that's what we mean by the direct substitution property. That the limit of x approaches a f of x, you just plug in a for x and you get f of a. Which you also might recognize is the condition of being continuous. Right? For a function to be continuous, this has to be true. So let's actually talk about that in the last 20 minutes we have. So without all the fancy words, what I'm really just saying is when you're finding a limit, you should just try plugging in whatever x is approaching and seeing if you get a real number. An example where that doesn't work is the example we started with today, right? If you do the limit as x goes to 0 of sine of x over x, if you just plug it in, it doesn't work. You get sine of 0 over 0, which is just 0 over 0, which is an indeterminate form, right? 0 divided by 0 does not equal 1. I mean, it can end up being 1 sometimes, but it is not always equal to 1. And that's because this function this function is not continuous. Right? There is definitely a point of discontinuity right there. So that's kind of the difference. Yeah, right. You can't plug in 0 because 0 is not a place where the function is continuous. So that's a counter example, or an example of how the direct substitution property does not work in this case, because we're looking at a place where the function is not continuous. Just like you couldn't take the limit as x goes to pi over 2 of tangent of x because you can't plug in pi over 2. At least you can't do it that way. There are other ways to think about that limit. Okay. So, continuity. Where to start? There's so many ways to kind of talk about this. Let's say, sorry, my brain is trying to do 2 different things at once with this example here. Yeah. So here are some pictures of functions that may or may not be continuous. And I'm gonna make them all continuous or not continuous at the point 2, 3. So here's one function. Here's a similar looking function. Here's a very different looking function. I get effectively something called this g of x, this h of x, and finally, let me get one more on here. Okay. So let me ask you guys, hopefully you can see my pictures all right. Do any of these functions look like they're continuous at the point 2? They do not. This one doesn't. I've got a little, right? I couldn't. So again, one of the ways people talk about continuity very kind of easily is, can you draw the graph without lifting your pen off the paper? And I couldn't do that for any of these, right? Right here, there's a little hole I have to jump over. I lifted my pen off the board. Here, there's also a hole, and I have to jump up here. Here, there's a giant vertical asymptote, right? I definitely can't draw that without lifting my pen off the paper. And here, there's what's called a jump discontinuity, where I go up here, and then I have to go down here. So none of these functions are continuous. And they're all kind of failing to have the one thing we need to be true, which I will say in a minute. But first I want to point out that for each of these functions, let's call this one, sorry, I know my function always kind of go here, k of x. I want to point out 2 or 3 things for each of these. Here, f of 2 does not exist. Right, if I try plugging in 2, I don't get anything out. Let me ask a different question though. What's the limit as x approaches to of f of x? What are the y values getting closer and closer to as the x values are getting closer and closer to 2? The y values appear to be getting closer and closer to 3, exactly. For this one, similar results actually. Here f of 2 does exist. F of 2 is equal to 4. And in the same way as this one, the limit here as x approaches 2 of f of x is equal to 3. Okay. This one over here, oh, sorry, I called it f, but it was actually g. This one here, the function definitely doesn't exist at 2. H of 2 is also undefined. And the limit really doesn't exist, right? In fact, I should talk about how the left-hand limit, so the limit as x approaches 2 from the left, is going, so as you approach 2 from the left, we're going to positive 3. And the limit as x approaches 2 from the right, we're going to negative infinity. If they were both going to the same infinity, we would say that the limit was infinity. It would still not exist because infinity is not a real number. So like, for example, sorry, just as a point of contention here, right? If this was my picture, like that, I would still say the limit as x approaches 2 doesn't exist, but I would also say the limit as x approaches 2 is infinity because it's getting infinitely large as we get closer and closer to 2 from either side. Still doesn't exist though. Lastly, this one, k of 2 is equal to, well, it's not equal to 2 because it's open there. It's equal to 3 because it's closed there. So k of 2 is 3. And here we also have a left-hand limit and a right-hand limit issue. So the left-hand limit, the limit as x approaches 2 from the left. If we approach 2 from the left, the function's getting closer and closer to 3. If we approach 2 from the right, sorry, I'm getting a little bit messy here. If we approach 2 from the right, the function's getting closer and closer to 2. And since the left-hand limit and the right-hand limit aren't the same, the overall limit does not exist. So here the limit as x approaches 2 of k of x does not exist. Just like it also doesn't exist here. The limit as x approaches 2 of h of x does not exist. All right. So here's the thing we notice about all these functions that are discontinuous at 2. Whether or not the limit exists or the function exists, we never have the case where both the function and the limit exist and are equal. Right? Here the function doesn't exist. Here the function and the limit both don't exist. Here the function exists, it's equal to 3, but the limit doesn't exist. And here, the function exists and is equal to 4. The limit exists and is equal to 3, but the function and the limit aren't the same. So for all of these things where we have discontinuity at x equals 2, the limit and the function don't have the same value. Right, if they both do not exist, we say they're not the same because we have no idea what they aren't anything. So this actually brings us to the point, which is that for a function to be continuous at a point, the limit and the function value have to equal each other. So that's actually how we define continuity. Now, So the function f of x is continuous at the point a comma f of a if the limit as x approaches a of f of x is equal to f of a. Now, this is a perfectly fine definition, but typically a lot of people will break it down into a 3-part definition. So when I'm thinking about something being continuous, there's actually 3 things I look for. Really, they're all in this statement here, but it's kind of easier to break it down this way. So the first thing we have to look for is we need the f of x. I really should say, I should back up. Continuous at the point a comma f of a. So the first thing we need is that f of a has to be defined, or exists, I should say. So to be continuous, f of a has to exist. The second thing that has to be true is that the limit as x approaches a of f of x must exist. This usually or often breaks down into having to check that the left and the right hand limits are the same. So there's usually a sub part here where we say, okay, does the limit as x approaches a from the left of f of x equal the limit as x approaches a from the right of f of x? And then finally, if the function exists at a, if the limit exists at a, then we have to check and see if they are equal to each other. Which is really what we started with up here, right? So does the limit as x approaches a of f of x equal f of a? That's the last thing we have to check. Really, you're checking all that when you're asking this, because if either one of them don't exist, then they can't be equal to each other. But this is the longer way, the more typical way of checking to see if a function is continuous. All right. Let's do an example. Often, these examples of continuous or not continuous functions are written as piecewise functions. So here's an example. Is this function sine, oh gosh, can I write the words? F of x is equal to sine of 4x over 2x when x is less than 0, and it is equal to x squared minus 5x plus 2 when x is greater than or equal to 0. Is this function continuous everywhere? Or really, we would just ask, is it continuous? So here's kind of some quirks about these questions. If I ask you if a function is continuous, I really am asking you, is it continuous everywhere? If I ask you if a function is discontinuous, I'm usually asking you where it's discontinuous. So here, there's only really one point we're concerned about continuity, right? I know that this quadratic function is definitely continuous everywhere it's defined. I know that sine of 4x over 2x, as long as x isn't 0, is definitely continuous everywhere. But I'm curious if the left-hand part of this and the right-hand part, right, if the left-hand part of this function left of 0 and the part right of 0, if those are actually kind of meeting up or if they're missing each other. So that's what we're going to check. So specifically, we're concerned if it's continuous at x equals to 0. All right, thing one. What's f of 0? If I plug in 0, what do I get? Well, where do I plug in 0? Do I plug in 0 to the top part or to the bottom part? Yeah, the bottom. Sorry, I had a question from someone else here. Yeah, I plug in the bottom. So I get 0 squared minus 5 times 0 plus 2, which is 2. And I plug it at the bottom because that's where x is equal to 0. And then I go on to the second part of my 3-part system for finding if a function is continuous at a point. I ask what the limit is. And in a lot of these, again, you're going to have to take the limit from the left and the limit from the right. So the limit as x approaches 0 from the right, I'm going to use where x is bigger than 0. And here I'm just going to plug it in because I can. I get 0 minus 0 plus 2, which is 2. Not surprising, right? We use this part of the function to evaluate f of 0. It's not surprising. The limit is the same. All right. And then I'm also going to do the limit from the left. So when I approach 0 from the left, I have to use the part of the function where x is less than 0. So that's going to be the limit as x goes to 0 of sine of 4x over 2x. And then we see that this is one of those sine limits that we just spent half the class practicing. So we know that this is going to be the limit as x approaches 0 from the left of sine of 4x over 4x and then 4x. This part goes to 1 and 4 over 2, right? The x's cancel. It's just 2. So the limit there is 2. So look, the limit from the left, from the right is 2, and the limit from the left is 2. So since the limit from the left and the right are the same, the overall limit does exist. So we can say, oh, that means the limit as x approaches 0 of this function is 2. And then the third part, which is where we kind of make our decision, we say, oh yeah, the function and the limit are equal. So we can say, I'm going to erase the top part here. Where is this part? So part 3, I would write something like f of x is indeed continuous at 2 because the limit as x approaches 0, sorry, not continuous at 2, it's continuous at 0, or if you want 0 comma 2, because the limit as x approaches 0 of f of x is equal to f of 0, which they're both equal to 2. But that's not really, the important part is this is equal to this. It doesn't really matter that it happens to be equal to 2. So that's how you would show a function is continuous at a point, is by showing that the function exists there, the limit exists there, and they're equal to each other.